other half of the machine is going to be the clamping side. And this is how we size our machines. When I say an 800-ton machine, I'm saying that machine can apply 800 tons of force. And so here again, this is really answering the question of, can I hold that die closed as I fill the die casting? And this actually has a very simple way of coming up with these numbers. What you do is it's really just the projected area of the casting times the metal pressure. And so typically if we run a metal pressure of about 10,000 psi, we could take an example and say, let's say I have a casting that's 100 inches squared in projected area. I multiply that times 10,000 and then I divide by 2,000 to convert to tons, and I'd find that that 100 square inch casting is going to need roughly a 500-ton machine. Now that will be at the very limit of what the machine can do, and so really I'd need something a little bigger. And so this is a great tool because I can run this little calculation as a die casting designer, and when I go out to get a quote or when I'm looking at what size machine is going to be needed, I know I'm going to be somewhere in the 500-ton range. So if someone quotes me saying this is a 2,000-ton part, I can say that seems a little big. And if someone quotes and says, well, really this can run on a 300-ton machine, then we can go back and say, can you show me your analysis and explain to me why it's going to fit? And so when we really look at sizing our machines, we want to balance these two variables and make sure that they all match up. And you want to keep in mind that not all die casting machines are the same. They're actually quite similar to tractors in the sense that they're all a little bit different. And so not every 800-ton machine is going to be identical. So one die caster might have a 600-ton machine that can make your part, and another die caster might have an 800-ton machine, which is the smallest machine they can make your part with. And so you want to keep that in mind, and that's why we give you this brief introduction to sizing these things. Now there's other things I need to be concerned about. It's not just enough to say I can hold that die shut and I can fill the die casting die, which is a PQ squared and a clamping tonnage problem. There's other problems we have to be concerned about. And so here are just some examples. These would probably be four of the biggest ones that I'd want to think about early on. One is my filling pattern and my plunger speed. So how am I actually going to fill that die? How's that metal going to flow? And is it going to flow in a good way or in a bad way? We can look at our venting and vacuum. It might not be intuitively obvious, but all the air that's in the system has to be evacuated in front of the metal. Otherwise, we're going to trap it inside the metal and create porosity. We also have to control the temperature of the die, both for die life as well as for controlling defects or characteristics of the process, such as porosity. And then finally, we pick die casting because we get great dimensional control, and so we have to at least factor in what variables do I have to control to achieve whatever level of dimensional tolerancing that I require. And so this is just one very useful exercise you can do as a designer, where what you're going to want to do is look at your geometry and say, you know, if I tried to fill this, how would I want it to fill? And again, the goal here is to push the metal from one side of the casting to the other in a nice uniform way. And by doing that, I can guarantee that I won't trap any air and that I'll get a nice surface finish on my casting. So if you look at these examples, you can start seeing some different ways or rules that you might be able to follow. For example, if you look at B, here we're trying to take the shortest path across that casting. If we took a longer path, obviously it gets harder for me to fill. And so we can really start understanding what this casting is going to have to look like just by looking at our design and saying, how would I like the metal to fill this casting? But it's not just that simple. I also have to worry about how I'm going to actually inject that metal, what speed I inject that metal at. And there's really two major parts of this process. One is my slow shot speed, which is really this velocity that I see, this VC, on this chart on the left-hand side. And then I have a fast speed, which is from P2 to P3 on that left side of the graph. And I want to focus just a second on the VC, or the critical velocity at this slow speed. What we're doing is we have this chamber that isn't completely full with metal. And so we have to fill it completely. And if we move our plunger too slow, we're going to create a little wave that's going to detach from the plunger. It's going to hit the other